Hello friends. So we are going to learn method of superposition by taking a simple example of propped cantilever beam. So figure here shows the propped cantilever beam where unknown forces are shown MA, RA and RB. Now we have also seen that this structure is statically indeterminate structure, and there are two possibilities to make this structure. The first step of the analysis is to make this structure statically determinate by removing the unknown which are in excess of the equilibrium equations. So in this structure, if you see, there are two possibilities. First is either you can remove support RB or you can remove the moment MA. If you remove the support RB, the structure becomes cantilever. But if you remove the moment MA, structure becomes simply supported. So both ways we can make this structure statically determinate. That is the first step of analysis of method of superposition. We have to make structure statically determinate by removing the unknowns which are in excess of the equilibrium equation. So let us consider first case where we are removing the reactive force at B. So you can see here is a cantilever beam. You can see that under the external load, now support B will deflect because now we have removed the support RB, reactive force at B, and by removing the roller support at B. So this beam will produce a deflection at the end, support B. These are the deflection shown in the downward direction, and we can consider downward deflection as positive. Now in second step, under the external load, we get the value of this deflection delta B dash. We call delta B dash is the deflection at B because of the external load Q. In step 3, in this method, now you remove the external load. Why? Because we have already considered the deflection because of the external load. Now we can remove it and apply the load because of the unknown reactive force which we have removed previously, which is RB. This force is also called as static redundant force. So in the next step, now of course now we are applying RB as your external load. This beam will again deflect in upward direction at support B, and let us call this deflection as delta B double dash. This deflection is in upward direction. We can consider this as negative. So in the next step, total deflection delta B in the original structure will be obtained by superpositioning the deflection of the earlier structure which is under the external load alone, which gives deflection delta B dash, and by superpositioning the deflection because of the unknown redundant force, that is delta B double dash. This superposition leads to the following equation, that is delta B is equal to delta B dash minus delta B double dash. Because in the original structure you can see that deflection here is 0. So we can equate here delta B is equal to 0. Now this equation is also called as compatibility equation, and by solving this equation we can get the unknown redundant force, which is the primary objective of this method of flexibility method. Now these values are well defined. Under the external load, you can get the formula given because for the deflections. Because of delta B dash, we get QL to the power 4 over ATI, and because of delta B double dash, we get RB L cube over 3 EI. So this is how the single degrees of freedom when static degree of indeterminacy is 1, the structure is solved. Now we will see in the next class when we remove the support, take the redundant force as ME. So you can see here, this is your beam. As I have mentioned, there are two possibilities. One is you can remove this support, second you can remove the moments. So in the process we are getting simple supports. So you know, under this external load, this beam will deflect as well as rotate at support A and B. So here we are more concerned about moment ME. So we will relate moment with rotation, because these are the corresponding variables. Because if there is a force, there is a deflection. When there is a moment, we need to calculate the rotation. So we have removed this MA and make structure simple support. Under the external load, this structure will have the rotation theta A. Now this was the first step to make structure statically determinate, and in the next step we remove the external load and apply one of the redundant as your force. So we are applying MA as your force. So under this moment, this particular beam will deflect, will have rotation in the upward, in the opposite direction. So there will be theta B here. So let us call this as theta A, this is theta A dash, this is theta A double dash. So to write the compatibility equation, in the original structure the rotation theta A is 0. By superpositioning these rotations at support A, by adding up these three quantities, we get equation theta A dash minus theta A double dash. If you consider the direction which is clockwise as positive, counterclockwise as negative, then you get theta A dash minus theta A double dash is equal to 0. Actually this is nothing but theta A in the original structure. By taking the formula from the table for theta A dash and theta A double dash, we can get the value of this is given by QL cube by 24 EI minus this is given by MA by L over 3I is equal to 0. And by solving this equation, we get MA is equal to QL square by 8. So the example which we have covered is single degree of freedom. Now in next class we will see the multi degrees of freedom example.